So now we come to the final bit that we need for the multilinear restriction problem, and that is the other end of the interpolation. And so this doesn't actually use the multilinearity at all. We're going to turn it into a linear problem and use some very old ideas. So this is the idea that you try and think about these extension problems as a Strickhart's estimate. So you have a distinguished time direction, because that's one that points in the normal direction, and you do a Strickhart's estimate to get your mixed norm. A very long history of doing this. And it really boils down to getting the L1 to L infinity estimates and the L2 to L2 estimates. The trick here is to have those other variables hanging around, and I need to deal with them. Okay, so this little part here is just rehashing the details of the kind of Thomas-Stein Strickhart's estimate. So for people who have worked with these kind of problems before, it would be pretty familiar. All right, so what do we do for this case? Well, firstly, we unravel the multilinearity. So just use Holder's estimate to get rid of it. We're now talking about linear objects, and we will just focus on E1. Okay, so the other M are exactly the same. So here's our parameterization, and we express it in terms of our distinguished variable T and our other variables. So we wanted to express it using a kind of Strickhart's estimate type thing, but we need to deal with the y-bar variables because we don't have curvature in them. So the first thing we do is a decomposition. Just trying to see how flat this is, the surface is with respect to the y-bar variables. Okay, so this gives us all options between being absolutely flat and being sort of very much not flat. So finally, you would be looking at x-bar direction is getting some significant time propagation. Just chop up the operators to match, and we'll have a look at each one of those. Now, the way we've cut up, we're giving up lambda to the epsilons everywhere. So this means we can just have a finite sum. It's going to be large. As you make epsilon small, the sum is going to get much, much larger, but it is always still finite. So this is just changing the variables and getting it into a nice form. So this form is good. It's almost what we need. Okay, what I really would like to do is freeze the y-bar variables. So they're the ones I'm just going to measure in L2. I'd love to freeze those and work in the other variables first, because they're the ones that I'm doing my LP norms in first, then take my L2 norms. That's my aim. I can't quite do that because Xi2 is paired up with time. And so that's why I introduced these new variables, tau and rho. Tau is sort of associated with rho and with time, and rho is dual to tau. So they just go in via a semi-classical identity. This is just an application of the stationary phase lemma. So a couple of things that we notice. When tau is greater than 2, you make an order lambda to the minus infinity contribution. Remember that everything is living on a ball of radius 1. So t is on a ball of radius 1. If tau is bigger than 2, then I'm going to be non-stationary in the variable rho. So I can just integrate by parts as much as I like. So this gets me something. It gives me a symbol that is tau independent. And so what I'm going to be trying to do is I'm going to be trying to sort of move everything that involves the Xi2 and the Xi tilde dual variables. I want to move those out and treat those separately later on. So I want to freeze the spatial variables associated with them. And to do that and write this in a reasonable way, I need to treat both tau and rho as input variables into an operator. Now, that's a bit annoying because tau and rho are dual to each other. And normally, if you have two dual variables in Fourier theory, you want one to be input, one to be output, and that will give you the sort of the correct L2 behavior. So what I'm doing here is I'm inserting a symmetrization, which basically trivializes the tau integral. And what I buy from that symmetrization is the ability to remember that tau and rho were dual to each other while treating them both as input variables. So this is just, it's putting some information back in a different way so that I'll be able to hang on to it when I factorize my operator. Okay, so I just go through here, track what that symmetrization means. And the really major point is I can write my TR in this format. So I freeze Y first, and I define a function for every frozen Y, and then I apply my inner operator. Now, my inner operator, it takes things in eta, rho, and tau to things in T and Z. So it allows me to do my inner LP norms. And then I do my outer LP norm, or my outer L2 norm in Y bar afterwards. So that's what I'm saying here is if I can control the mapping norm for IR, the inner operator, and the L2 norm for F, then I can glue those two together and get my operator norm for T. So the rest of it is just computing those two things. So the bound for F, this is just write it out longhand and integrate by parts a lot. Okay, so there are multiple points at which this is going to be non-stationary. Firstly, integrating in rho, this picks up the symmetrization. This is just remembering that rho and tau are dual to each other. Then you do your integration by parts in each of your Y variables, and that restricts the xi and the zeta things to be close to each other. The result then follows from Schur's test. So this is just extracting the oscillation. Now, finally, we turn to IR, and this is the one we're going to treat like a Thomas-Stein-Strickhart's type estimate. So again, we write that out, and again, there's a quick little argument that shows that if we fix T and S, and we look at, say, a fixed displacement, we have to have this relationship between T minus S and the two displacements. So again, this is just extracting that decay, remembering the dual behavior between tau and rho. So we get to knock some terms out of the sum, and we get to knock out exactly the right number of terms to make up for the fact that we introduced these variables in the first place. And so that's what is happening here, is I'm just knocking out the factors that I had to put in to introduce those variables in the first place. But this means I'm down to sort of a lower dimensional extension operator. So I can estimate the L2 to L2 norm just by recognizing that this is like TT star of two extension operators. So I get that. Then to get the L1 to L infinity, I just do a very standard calculation. That is, I do a stationary phase calculation. And so this is the one that appears in the standard Strickhart's Thomas-Stein type results. Okay, so this is why we needed that curvature condition, which essentially means that all of the sections that we take of this original sigma, we take the sections in our missing variables, they're all curved as things sitting in a lower dimensional set. So that's now really, really standard. Okay, so you're just kind of turning the handle on this thing now. You've got the two estimates, you interpolate between them. You use Young's inequality to do the T minus S integral. So again, this, once you've got it in this format, it is a really stock standard type estimate. Pick up some logarithms. That's just the usual integrating 1 over T dt type thing. Finally, you need to treat the R is equal to 0 case a little bit differently because you can't do the change of variables, but it really isn't that different. You introduce these variables again, just without doing that change of variables on xi2. And because it's flat, this term really isn't doing anything at all. this term is basically constant, and we can control it very nicely. So that is just following through. And again, you've got the same sort of idea, right? You're going to fix y, apply it in an integral, which is pretty much the same integral as we had before. And then we will integrate in y later on. So this just finishes it up for t0. The final bit is in the d-1 case. So that was one that looked a bit different in the interpolation. It turns out to be exactly the same. You just need a little holder argument to get there. So for this one, I am going to apply Holder's inequality to get from my multilinear to linear. But previously, I applied my Holder and I applied it with equal weighting for each of my factors in my product. In this case, I'm going to weight differently whether it's a t variable or a y variable. So for each m, there is one time variable, and all the others are kind of space variables. So they get a different weighting, time and space, and this is just the numerology for that. And the point is that this different weighting reduces all of the space variables to L2 and puts the time variable at L4. Then you just follow the same reasoning through. And L4 is exactly the correct thing to be measuring time in for this. Okay, so again, there's this numerology that comes through out of the Thomas-Stein type estimate. And for the d-1 case, L4 is precisely what you want to be measuring. And that, in terms of this problem, really isn't surprising. This is a very sharp theorem. The examples are very sharp. So we expect all of the bits and pieces that go into it to be sharp as well. So it's not at all surprising that this turns out to be the precise sharp thing for the Strickhart's norm either. And finally, you just get to state that altogether, that you have up to your epsilon loss, the correct estimate in this mixed transversality curvature case.